We will now tackle the last section of the chapter. What is really nice about this section is that it will open up the discussion of chapter 5. We're going to be talking now about antiderivative. What does that really mean? Suppose that we have the function f of x equals to 2x, and we are being asked to find another function such that its derivative is equal to 2x. For example, let's find a function. I'm going to call it a big f of x. And what I want is for f prime of x to equal to little f of x. In other words, to 2x. So I'm wondering, what will that function be? I need a function, big F, such that its derivative is equal to 2x. And this is a very simple question to ask. If you quickly think about it, the function has to be x squared. So here, I conclude that big F of x is going to be equal to x squared. If you quickly differentiate x squared, you're going to get 2x. In a similar way, I can go ahead and let's say start with little g of x. G of x, let's say it's equal to x squared. Why not? Now the question is, can I find another function, let's call it big G of x, such that the derivative of big G of x is equal to little g of x. In other words, 2x squared. So what function do I need to differentiate so that I get x squared? If you think a little bit more, you may have to put a little bit more effort here to think about it. You're going to come up with big G of x happen to be equal to 1/3 x to the third. So in this case, what happens is, imagine that you take this function right here, big G of x, and you differentiate it. Using the power rule, you bring the exponent down, you multiply it with 1/3, you're going to get 1, and then you subtract 1 from the exponent, and that's how you nicely get 2 as the exponent. Let's do one more. Let's say that now you have little h of x, and little h of x is equal to cosine of x. Why not? Then the question is, how do I find another function, let's call it a big H of x, such that its derivative, h prime of x, is equal to little h of x. In other words, equal to cosine of x. And then if you think about the trigonometric functions and their derivatives, it's pretty easy to realize that big H of x has to be equal to sine x. So then, we will say that big F of x, big G of x, and big H of x, all of those three functions are called antiderivatives. Okay? In other words, the antiderivative of little f of x is big F of x. The antiderivative of little g is big G. And the antiderivative of little h is big H. So pretty much finding an antiderivative whenever you are given a function is to try to find another function such that when you differentiate it, you get the given function. It's kind of undoing differentiation. In other words, you're given one function. This is a derivative. And what you have to do is you have to go ahead and find the function that you need to differentiate in order to get the given derivative. Now then, we're ready for our first definition. Definition number 1. Practically, I'm just stating here in a more formal way exactly what we discovered a few minutes ago. If little f and f are two functions, and we know that the derivative of big F is equal to little f of x, then we're going to call big F of x the antiderivative of little f of x. And just repeating myself, for example, if, let's say, you're given that little f of x happens to be 2x squared, then that implies that big F of x, the antiderivative of x squared, will be 1/3 x to the third. Now, I said an antiderivative. My question now to you will be, is this the only antiderivative of x squared? Is it possible for x squared to have a different antiderivative? About it, it is possible. For example, I can go and write big F of x. Actually, let me even call it f sub 1. I'm going to call this one here, the previous one, f sub 0. F sub 1 could be 1/3 x to the third plus 1. If you differentiate f sub 1, because the derivative of a constant is equal to 0, that derivative will go back to x squared. Both of these, f sub 0 and f sub 1, they have exactly the same derivative of x squared. In the same way, I can generate another antiderivative. S sub 3 of x could be equal to 1/3 x to the third minus square root of 5. Again, the square root of 5 is a constant. The derivative of a constant is equal to 0. So in this way, you can hopefully tell now that I can have infinitely many antiderivatives. So this particular function, little f of x, x squared, has infinitely many antiderivatives. So an antiderivative is not unique. You don't just have one antiderivative. Pretty much by adding any constant or subtracting any constant, you preserve the same derivative. So if a function has an antiderivative, pretty much it is safe to say that it has infinitely many, because you can create infinitely many antiderivatives by adding or subtracting a constant. So then, if you are given, let's say, a little function, that's little f of x, and you know that this is a derivative of some other function, so then after a little bit of thought, you come up with big F of x as the antiderivative. Then you immediately know that every single antiderivative of little f of x will be y equals big F of x, the one that you found first, plus c. And again, this is a constant. And this constant can be a positive number or it could be a negative number. In other words, we're going to say C can be any real number as long as you keep it a constant. So this will give you infinitely many antiderivatives. For this reason, we can also call it, if you notice, the author calls f of x plus c, he calls it the general antiderivative. Why general? Because general means that this expression right here covers every single antiderivative. But sometimes you may just pick one or two, so you may have specific antiderivatives. So for example, a specific antiderivative for the function that we just discussed over here above could be f sub 1 of x, which is 1/3 x to the third plus 1. This is a specific antiderivative. But as soon as you replace the 1 over here with just c, implying any possible real number, then in this case, you are including the general antiderivatives because you're accounting for every single possible constant that you can think of. Here what we have, again, is little f of x being x squared, and I have big f of x, which is 1/3 x to the third plus c. This is the general antiderivative. And what we did over here is to provide a few sketches of some of the particular antiderivatives. If you notice, this is the base one where c, the constant, is 0. And then by adding 1, all that we're doing is shifting the center graph upwards. It's a vertical shift, a vertical translation by 1 unit. So that doesn't change the slope of the tangent lines at a specific value of x. In other words, what I'm saying is the following. If I pick this particular value of x right here, that takes me to this point on the graph. And let's say I draw a tangent line. Then if I now go to the upper antiderivative, I'm keeping the same x value, and then I draw a tangent line, you notice how the two tangent lines are parallel. That means that the slopes are exactly the same. And I would like you to remember that the graphs that we're sketching here are the big f of x graph, right? This is big f of x when c is equal to 0. This is, let's say, big F sub 1 of x when c is equal to 1 in this case. So that takes us to this one right here. So what happens is that when I take the derivative of big F of x, if you remember, the derivative f prime of x has to be equal to little f of x. So then the slope of these tangent lines over here is little f of x. But again, the slope doesn't change. The slope is exactly the same throughout because all that I'm doing by adding or subtracting c is performing a vertical translation. So as long as I keep the same x value and I calculate the slope of the tangent lines are going to be parallel. So those slopes are going to be the same. That means that the derivative of those big f functions will be little f of x throughout. Let's have fun, a bit of more fun, playing with other antiderivatives. For example, if you are given little f of x to equal, say, secant squared of x, then you know that an antiderivative will be equal to tangent of x, right? If I differentiate tangent, I'm going to get secant squared. And if I decide to add c, then this is now giving me the general antiderivative. I am getting every single possible antiderivative I can think of just by adding my constant. If I now choose, let's say, little h of x to be cosecant squared of x, then an antiderivative would be equal to negative cotangent squared of x. If you differentiate negative cotangent squared, you're going to get cosecant squared. And by adding my constant, I now take a specific antiderivative and I turn it into a general antiderivative. If I take little g of x equals to e of x, this is the simplest possible because the antiderivative of e to the x is itself, right? Keeping in mind that every time that you differentiate e to the x, you don't get anything new. You get e to the x back. And then other interesting ones, what would happen, for example, if you're given little f of x, which is a power function? And I am really hoping here that when you think about this power function, x to the n, and you think about what could be an antiderivative of x to the n, I'm hoping that you're going to think about the power rule for differentiation, but backwards. If you remember, back then, I don't know, chapter 3, I believe, if we had y equals x to the n and we wanted to find y prime, the rule said to bring n down as a coefficient of the power function, take x to the n and subtract 1 from the exponent. Whenever we are undoing differentiation, we're going to do the opposite of subtraction. We're going to go ahead and do addition in order to get the antiderivative. So we're going to be adding in the exponent. And instead of multiplying, we're going to be performing division. For example, we start with x, we take the exponent and add 1 to the exponent, and then we're going to go ahead and instead of multiplying, we're going to reverse multiplication by dividing by n plus 1. So if you notice, if you actually differentiate this expression using the power rule from chapter 3, you're going to bring the exponent down, so you're going to get n plus 1. N plus 1 will cancel the n plus 1 in the denominator, and when you minus 1 from the exponent, you get n, and there you go, x to the n. Now, to get the general antiderivative, all that I have to do is to add c at the very end. Now, I'm hoping that you also notice that this is valid provided n does not equal to negative 1. If n is equal to negative 1, you will be dividing by 0, and you know that this is not allowed. That's not going to give you a real number. So in other words, what we are saying is that if we happen to have f of x equals x to the negative 1, which is equivalent to saying 1 over x, we cannot find the antiderivative by using the power rule in reverse. We cannot do that. So we're going to have to put a little bit of thought then. Does 1 over x have an antiderivative? In other words, again, if f of x is equal to 1 over x, can I find an antiderivative? I mean, if you would like to pause this video right now so that you think about it on your own, you can do that. That would be a good idea. Pause and think. 1 over x. I cannot use the power rule in reverse because I will be dividing by something that has 0 because n is equal to negative 1. So what do I do? Do I have an antiderivative or not? Well, hopefully after some thought, you may remember that if you take the natural logarithm, in other words, ln of the absolute value of x, the derivative f prime of x of ln of the absolute value of x is equal to 1 over x. I remember that we actually proved that a few months ago. So then 1 over x, right here, 1 over x has an antiderivative. The antiderivative is equal to ln of the absolute value of x. And if I want to find the general antiderivative, then I will write big F of x as ln absolute value of x plus c. So this expression is the antiderivative of 1 over x. So far, we have been using uppercase letters to represent antiderivatives. Big F of x, big G of x, big H of x. But now we're going to transition into a fancier, a nicer notation that is going to become pretty much our notation for the second half of this course. You remember that if we give you little f of x, the general antiderivative is another function that consists of big F of x, the antiderivative, plus c. Remember, this was the general antiderivative. Okay? Big F of x plus c. Big F of x plus c. Instead of using, though, big F of x as a notation, we're going to go ahead and use the following notation. Something that looks like a very long S, little f of x times dx. This elongated S is called an integral sign. As soon as we discuss sections 5.1 and 5.2, you will see exactly why this elongated S for sum, this piece over here is called a differential. And for now, the differential will just be notation. Again, this will make more sense after we do section 5.2. And f of x right here is the typical little f of x that we give you. This is the little f of x whose antiderivative you are trying to find. So this notation is equal to the general antiderivative. So whenever we give you, let's say, the integral of sine x dx, all that I'm asking you here is to find the general antiderivative of sine x. Find the general antiderivative. Find the function such that when you differentiate it, you get sine. Exactly what we were doing just now. I want to find the general antiderivative, so then I know that I have to differentiate negative cosine of x. The derivative of negative cosine of x is going to give me sine x plus c. By adding the c, I now have the general antiderivative. So this is all what the notation means. This integral notation means that you have to find the general antiderivative of the little function that appears after the elongated s, after the integral notation. If, let's say, now you have the integral of 1 over x dx, you're going to look at the little function right here, 1 over x, and you know that what we're asking you to do is to find the general antiderivative of 1 over x. So think about a function so that when you differentiate it, you get 1 over x. Hopefully you're thinking of ln. So then this will be equal to the natural logarithm of the absolute value of x plus c. Honestly, that's all that it means. It's just notation for now. Now, let's say that you're being asked to calculate the integral or the general antiderivative of a quadratic, something like x squared plus 2x plus 1 dx. Remember right now, this over here is just notation. So this is what we have. This is the function, but now this function is a quadratic, so it has 3 terms. How do we find another function so that when we differentiate it, we get this right here? Well, properties of integrals, they have the same properties as derivatives. In other words, if you have a function that is made up of several terms, you can go ahead and you can find the antiderivative of x squared, the antiderivative of 2x, and the antiderivative of 1 separately. In other words, you can break up the sum into 3 separate little functions. And then you can individually find the antiderivative of each function. Same idea as when you were differentiating. So in this case, I can have the integral or the antiderivative of x squared dx plus the integral of 2x dx plus the integral of 1 dx. Another thing is I have this numerical coefficient. Just like with derivatives and even limits, you know that you can go ahead and bring the numerical coefficient in front of the integral sign. So I can have 2, the integral of x dx plus the integral of 1 dx. And now what I am going to do is I'm going to find the general antiderivative of x squared, the general antiderivative of x, and the general antiderivative of 1. So x squared, that means that an antiderivative of x squared will be x to the third over 3. I'm using the power rule in reverse. Remember, you take the exponent right here and you add 1, so you get 3, and then you divide by 3. Technically, I should add my C1. Plus, over here 2 will stay outside. What is an antiderivative of x? Using the power rule in reverse, I take x. The exponent is 1, so when I add 1, I get 2. Now I divide by 2 plus another constant. And notice how I am writing c sub 2 to make it different from c sub 1. And then over here, plus, if I have 1, what function do I have to differentiate to get 1? Hopefully this is easy. That will just be x plus c sub 3. So now, collecting all the terms with x and then all the constants together, we're going to have, now here I have to distribute these two, so we're going to have x squared plus 2c2 plus x plus c sub 3. That will give me x to the third over 3 plus x squared plus x plus, I actually lost C1 before. I apologize. I just forgot to write it down. We're going to have 2C2 plus C3 plus C1. In general, yes, you do have 3 separate constants, but nobody really worries about the individual constants. What is done in this case is that all 3 constants are just represented by one single constant. They all collapse to C. So what you really write is just x to the third over 3 plus x squared plus x plus C. And that's how you find the antiderivative or the general antiderivative of the original quadratic that you were given. And that makes perfect sense. If you were given a quadratic, its antiderivative had to be a polynomial with degree 3. Suppose that you're given the integral of cosine of 3x plus 1 dx. Again, this is little f of x. And what you want to do is you want to go ahead and find the general antiderivative of cosine of 3x plus 1. I want you to think about the fact that we have a composite function here. We have cosine as the outer function and an inner function that is linear, 3x plus 1. So if you were asked to differentiate this function, then you know that you would have to apply the chain rule. For example, then, the first thing that I want you to think is about cosine. Which trig function do you have to differentiate to get cosine? Hopefully, you're thinking sine. Let me do some work here on the side. That means that the derivative of sine is cosine. So that's an improvement. Now I have to think, how am I going to handle 3x plus 1? I need to have 3x plus 1 in there. So imagine that I just write 3x plus 1. All right, what happens if I actually stop here and I claim that this is my antiderivative? Is this really the right antiderivative? Let me differentiate it to see if I get this stuff over here. Well, if I differentiate sine, I'm going to get a cosine of 3x plus 1. So that's awesome. I get cosine of 3x plus 1. But now I do have to apply the chain rule. So I'm going to have a factor of 3. And if you notice, over here, I don't have a factor of 3. I just want to have cosine of 3x plus 1. This factor of 3 came from applying the chain rule. So then, in order to eliminate this factor of 3, that means that the original equation has to have a factor of 1/3. In other words, what I need is sine of 3x plus 1 divided by 3. Now, if I differentiate this expression, I'm going to get exactly the expression, the little f of x that was given to me as my integral. So to complete the question, I will say that this integral is equal to sine of 3x plus 1 divided by 3 plus c, because the integral means the general antiderivative. So I have to add c in there. Therefore, in conclusion, if I am asked to calculate the integral of cosine of kx plus m, I'm going to now be general, and I am going to work with variables, little k representing what used to be 3 before. M is just any other constant, what used to be 1 over here. The general antiderivative will be, in this case, sine, because the derivative of sine is cosine. Then you're going to have the same line, kx plus m. But then remember that you need to divide by k so that you get rid of k whenever the chain rule is applied. And then you're going to have plus c. If you're given to calculate the integral of sine of kx plus m dx, so let's think which function has a derivative of sine x. So if I consider negative cosine, the derivative of negative cosine will be positive sine. And then the linear expression will stay there, but now I have to divide by k, and I have to add c. If you want to try, differentiate this expression. If you differentiate that expression, you're going to get this one right here. The last part of this discussion here, we'll talk about differential equations. I've written down our second definition about what a differential equation is. So a differential equation relates, so it's connecting an unknown function and its derivatives. We have been working all along with the simplest differential equation. Whenever you're given a little f of x and you find an antiderivative, so that big F of x, the derivative of big F of x is equal to f of x, you have a differential equation. This is a simple example over here of a differential equation. Why? Let's think about it again. A differential equation relates a function that is unknown and its derivative. So the unknown function here is big F of x, right? Usually we start with little f of x, and little f of x represents the derivative. So big F of x is the function that we don't know. We usually have to look for that function. Again, which function do I have to differentiate to get, for example, sine x? And there you are thinking about which is the function that needs to be differentiated to get sine of x. So that's the unknown function. However, even though big F of x is unknown, you know something about its derivative. You know that the derivative of big F is equal to little f of x. And that's what makes it a differential equation. Because in this simple equation right here, you are talking about an unknown function. And all that you know about that function is its derivative. You know that the derivative of big F is little f of x. The derivative of big F is little f of x, but you don't know big F of x. You have to find it. You have to think about what that function is. So imagine that as an example over here. Let's say that we are given a very simple differential equation. If you don't mind, I'm going to call big F of x little y. So what I have is that dy by dx again, dy by dx is f prime of x, big F prime of x. I know that the derivative of this mysterious function, f of x, is equal to 4x to the 7th. So again, the derivative of big F of x is 4x to the 7th. Remember, the function big F is unknown. I know that we can use the power rule in reverse to find the function, but at first, when you begin, you don't know the function. All that you know is that its derivative is equal to 4x to the 7th. So this is an example of a differential equation. So now the question is, can you solve the differential equation? Solving a differential equation means, again, find all the functions that you can differentiate to get a derivative of 4x to the 7th. This is the same question as asking, what is the general antiderivative of 4x to the 7th? So in other words, the solutions of this differential equation will be all antiderivatives. So it's like asking, what is the integral of 4x to the 7th dx? And then I go using the power rule in reverse. That will be 4x to the 8th divided by 8 plus c. So that's going to give me, if I simplify, that will be 1/2 x to the 8th plus c. So now I know that if I have the differential equation dy by dx equals to 4x7, then the solutions, all solutions, are going to be y equals 1/2 x to the 8th plus c. All of these functions over here, once I start changing the value of c, will give me this derivative. If I differentiate y, I am going to get 4x to the 7th. So I found the solutions of the differential equation. Sometimes, though, there are going to be some problems where they may want you to find a specific solution, not just to have the general solution. So what they're going to do is they're going to give you what is called initial conditions. And initial conditions is just a fancy way of giving you a point where one of the solutions passes through so that you can actually find the specific equation. For example, let me explain so that you can put it into perspective here. Let's say that we tell you y of 0 is equal to 4. That means that what you want is you want the particular antiderivative that passes through the point 0, 4. Right now, you have the general antiderivative, all the infinitely many possible solutions you can have. But now you want the solution or the curve that passes through the point 0, 4. So what you're going to do is to substitute 4 for y, then 0 for x, and that will allow you to find the value for c. So then you conclude that the specific solution will be y equals 1/2 x to the 8th plus 4. So this is now a specific solution. This is just one of those curves. Out of the many curves that you have, the infinitely many curves, this is the one that passes through the given point 0, 4. This is the one that they wanted us to identify. This is example 8, the last example in your textbook. And I thought that this is a very nice example because you're going to see the connection between position, velocity, and acceleration only in reverse this time. because remember, it is all tied up to antiderivatives, which is the opposite operation of differentiation. So in this example, we have that a car traveling with velocity 24 meters per second begins to slow down at time t equals to 0. So as soon as we begin, for example, our stopwatch, for example, then we know that this is when time is equal to 0, and that's when the car will start slowing down. So it begins to slow down with a constant deceleration of -6 meters per second squared. And negative meaning exactly the slowing down, right? The velocity is decreasing. A says, find the velocity v of t at time t. And then B, find the distance traveled before the car comes to a halt. So let's do A first. Find the velocity v of t at time t. So let's think here. We were given the acceleration. A of t is equal to -6. Let's remember again that the derivative of velocity is equal to acceleration. The derivative of velocity is acceleration. So if I have the acceleration and I want to find the antiderivative of -6, in fact, let's find the general antiderivative, then in order to get velocity then, what I have to do is find the function so that when I differentiate, I get -6. This is again thinking backwards. Now from acceleration, I want to go down to velocity. So then velocity will be the integral of a of t dt. Since now my independent variable is t, in my differential, I put t. Again, this is just a fancy notation for saying find the general antiderivative of acceleration. So that will be the integral of -6 dt. Again, I can bring the negative outside of the integral, and then all that I have to do is think of which function do I differentiate to find 6, or I can just use the power rule in reverse. So this will be -6t plus c. Now, they did give me an initial condition. They told me that when time is equal to 0, the velocity is 24. So this is something that I know. In other words, I know that v of 0 is equal to 24. Again, the initial condition of my relationship here. So I know that v of 0 is equal to 24. That means that I can go back to my antiderivative, my velocity function, and I can substitute. I can say 24 is equal to -6 times 0 plus c. So then c is going to be equal to 24. In other words, I conclude that the specific antiderivative that we're working with is -6t plus 24. And that's how I get the velocity, by knowing the acceleration. In part B, they're now asking me for the distance, so I have to go another step backwards. I remember in this case that distance, or if you want, let's keep using s of t. If you remember, s of t was the notation we were using back in chapter 2 or 3. S of t will be equal to the integral of the velocity, d of t, right? In order to get velocity, we used to differentiate s of t, if you remember. The derivative of s of t was giving us velocity. But now we're going backwards. So velocity, if we're going backwards, the antiderivative of velocity will give us position. the antiderivative of velocity is going to give us position. So what I want to do now is to replace v of t with negative 6t plus 24. And then again, because the independent variable is t, I'm going to have dt. And then remember that I can split the integral, negative 6t over here, dt, plus the integral 24 dt. And then the numerical coefficient can come outside of the integral, t dt, plus, because there's no variable here, I'm just going to leave the 24 inside. So, using the power rule, I know that the antiderivative of t is going to be t squared over 2 plus the antiderivative of 24 will be 24t and then plus the big constant. So that is going to give us s of t. Simplifying a little bit, actually I can simplify a bit more. We're going to get negative 3 t squared plus 24t plus c. And now we got the position function. Now, if we look back at the question, part B says to find the distance traveled before the car comes to a halt, before we stop. So from the moment over here, when we started our stopwatch, when t was equal to 0 seconds, until the car comes to rest, I want to be able to find that position. Right now I have a general position. What I need here is to try to see if I can find what c is equal to. If you remember in part A, they gave me an initial condition. They told me that at t is equal to 0, the velocity was 24. Unfortunately, in part B, they didn't do that. They didn't give us the distance when t is equal to 0. So because we just want to find the distance from whenever we started at t equals 0 to whenever we come to a complete stop, right? It doesn't really matter what exactly was, what number represents distance, whether it was at 20, whether we had covered 23 meters or 100 meters, that's irrelevant. I can always assume that when t is equal to 0, position was 0 meters, for example. So I can always say, without making any harm here, I can say assume that s of 0 is equal to 0. Because what I really want is this distance, exactly the distance after we started our stopwatch at t is equal to 0. So if I let t is equal to 0 and set everything equal to 0, imagine that I do this, negative 3 times 0 plus 24 times 0 plus c equals to 0, I find that c is equal to 0. So then that tells me that I can just make my position function to be negative 3t squared plus 24t. And this is the one that we're going to use. When the car comes to a stop, that means that the velocity is equal to 0. So that's how we're going to go ahead and find that time. We're going to go back to velocity. If you remember, v of t is equal to negative 6t plus 24. We're going to take negative 6t plus 24, and we're going to set that equal to 0, and we're going to solve for t. So negative 6t is going to be equal to negative 24. T is going to be equal to 4 seconds. So this is when the velocity is equal to 0. And now, by substituting 4 into position, that will tell us now that the distance traveled from the time that we started our stopwatch to whenever the car stopped is going to be equal to 48 meters.